Hello everyone, and welcome back to the class. So last class, as you recall, we talked about sklearn, more about sklearn. We talked about how to select the best model among a given set of models. We talked about bias and variance and what is the relationship between the bias and variance. Mm, We also talked about different kinds of curves that can help us diagnose how our model is performing. For example, the validation curves, uh, which looks like this. So basically, we plot the score on our training data and our validation data as we change parameters of our model, and we find the point where both of them are maximum. Right. Then we talked about learning curves, which um, are again like how does our model uh, change as we add more data to it, right? How fast does a model learn? Right. Learning curve. So this is a learning curve. Yeah, that was again validation curve. Yeah, learning curve. Then we talked about grid search and how we can use grid search to find the best estimator to tune our hyperparameters and everything for our model. Then we talked about feature engineering. So basically, one second. Yeah, so we talked about feature engineering. Uh, what are the different kinds of things that you need to do so that like you make your data set numerical so that your computer will understand basically what is going on. Mm. So how to convert categorical features, how to encode categorical features using like one hot encoding and everything. We talked about text features, how to make matrices out of text using TF-IDF, how to use images. So that's something that we didn't discuss, but you can follow these links to check out how it works. Then about derived features, so basically features that are uh, some combination or something of our own data. Then we talked about inputting missing data and also how we can create pipelines in sklearn so that we can train models. Okay. So after all that, today we have come to the final module of the course. So today's today basically you have learned everything that you had to learn from the course about Python, about data science, and about all the different kinds of packages in Python that you can use to perform data science. Okay. So now, in the last module, what we'll do is we'll do a sample project. So basically, we are given a data set called IBM HR Employee Attrition Analysis and Prediction. So it's a data set put up by IBM. It contains 35 different features of employees along with their attrition. So attrition is basically if they left the company or not. Okay. So this is a fictional data set that was created by IBM data scientists. You can download it using this link. So I'll show it. Yeah, you can basically use this link to download it. So it tells you more about the data and how it is. What are the different, what do you say? What are the different features and what are the different values? It gives you like the distribution and all slightly for different values. So Kaggle is a nice website to try out different projects in data science. So it has a lot of data along with a lot of people who have these Jupyter notebooks or other codes explaining projects. Okay, so basically there'll be a lot of codes where people have tried to answer different questions or tried to analyze this particular set of data. Okay, so basically, yeah, using naive Bayes, let's say, then imbalance data. So that's something we'll talk about later today. So anyways, that was the introduction. So basically, we are given this data set, and our objective is to build a model that can predict if an employee is going to resign or not. Okay. So we need to figure out which of these features or factors are important for predicting attrition, and then we need to find the best model that can perform this. Okay. So that's it. Then there are few suggestions for bonus projects, which we'll come back to later after we are done with the project. So basically, yeah, as I told before, this is the link. And our objective is to build a predictive model which can predict if an employee is going to resign or not. Okay. So the basic methodology that we want to follow here is uh, we have to build a model that which can predict if an employee is about to quit. Okay. We'll first look at all the different variables that are available to us or all the features that are available to us. We'll do some plotting and try to infer something about the relationship between these different variables in the exploratory phase of our analysis. Okay. Once we have our exploration sorted out, we will decide on some of these features to use for our models or maybe modify some of the features for use and things like that. And then finally, we will go ahead and build a model and then test how good it performs. And we can then subsequently improve on the model. Okay. So first we need to import all the libraries. So as we have learned about most of the libraries, we'll import all these different things. So basically importing OS, pandas, some pandas submodules, matplotlib, seaborn, and numpy. Okay. And this is basically setting some parameters for the plotting. So I want the label size to be 12 points, X tick and Y tick. Basically, the numbers on the X and Y axis to be 10 points, and I want the figure size to be this much, and things like that. So you can ignore these or you can run these, doesn't matter. Okay. So first, what we'll do, we'll load the data. So I have a CSV file. I'll send you the CSV file. So first what we'll do, we'll read the CSV data. So here's the name of the file. So the file is basically in the same directory in which this Jupyter notebook is there. So I don't need to add any directory. I just need to do pandas.read CSV and then provided the name of the file. It'll read it and store it in a data frame. And then we are basically printing the dimensions of the data frame. So when we do emp data or dot shape, we get what is the row and column as a tuple. Basically, we are doing this. We are getting the row numbers and the column numbers, and we'll substitute here. So we'll get to know how many rows and columns are there in the data. So basically, there are 1470 rows of and 35 columns. So as mentioned before, the data set had 35 features. So basically, we have 35 columns. Right. Then more we can look at what is the other information we can see from the data. So if we do emp data or dot info, we see what the different columns are. Okay. And this attrition is a target variable that we want to predict. Okay. Rest everything is basically variables that we'll use to predict the attrition. As we can see, all of them have almost 1470 values. We see the data type and we see what are the names of the different columns or the features. Okay. To get some basic statistics of the numerical features that we have, we can do mdata.org.describe. So it will give us what is the count for each column, what is the mean, standard deviation, minimum, 25th percentile, 50th percentile, 70th, 75th percentile, and maximum. So basically, we can look at the mean and the variance of our data by numbers. Okay. So yeah, we can see that almost all of them have 1470 points. Some of them are, what do you say? Some of them are nice. So there's a mean, there's a standard deviation, and the data is well distributed. But some of them are not like that. For example, employee count, because employee count is basically a has the value of 1 for every employee. We didn't look at the data. So what we'll do is empdata.org dot head. We'll take a look at the data. Okay. So basically employee count is 1 for everyone. Okay. So that's the number of employees or something. Counter kind of thing. Again, like education, uh, and environment satisfaction and things like that are basically categorical features that are given a number. For example, education can vary from 1 to 4 or 1 to 5 or something. One might be below college, one might be bachelor's, one might be master's and things like that. So like it's basically categorical data, but there is some ranking to it. Or environment satisfaction can be low, medium, high. Okay, low, medium, high, very high, or very low, or something like that. So low will be 1, medium will be 2, high will be 3, very high will be 4, and so on. Right. So that's it. And but since all the data in these rows are also stored as numbers, pandas also describes them when describing because these are also counted as numerical features. But we shouldn't ideally look at these columns. Okay. Where like the value is basically the same. Another thing is the standard hours where the mean is 80 and there's no variance. So basically it means all the values in the row are 80. So we don't want things like this because when we are trying to build a predictive model, we want to use features which have some variance so that like when these variants between different features interact, they like tell our model something. Right. So if you have a variable which goes from 0 to 10 or something, so our model can make different predictions for 0, 1, 2, 3, and 10. But if you have a variable which just has only one value, 80, then our model can't basically be using that particular point to make any predictions because that will always be 80. It will not vary. Right. So we don't want things like this, things that have zero variance columns. So that's one column. Then another is employee count. Then, as I mentioned, there are some columns like um, job level or job involvement or environment satisfaction or education, which are like numerical categorical variables. Okay. So now we'll also look at the categorical features. So basically what we need to do, describe, and then here you write include, and in bracket you write object. So basically we want to include only the object data types. Okay, not the numerical features. So now object data types, we have these few variables. Attrition is basically a target variable which has two unique values, yes and no. Hmm. Then apart from that, what else? Over 18 has only one unique variable. So again, this feature won't have any variance. So we will not be using this in the model. Okay. So basically what we see from now is that employee number we can remove because that's unique for everyone. Right. Employee number is basically 1, 2, 3, 4, 5, 6. That's unique for everyone. And we don't want our model to overfit. So we don't want our model to know the exact identity of every person, kind of. Right. Otherwise, it might just learn that. So generally, we don't include ID. Then the other thing is employee count, which is only 1 for everyone. Again, that is zero variance. Standard hours has zero variance, and over 18 also has zero variance because it just all three of them just have one value. So these uh, columns we can remove from our analysis when we are building a model. We need to keep that in mind. Okay. Now we'll take a look at the distribution of the attrition variable. So we'll do sns.hisplot. We'll plot a histogram for frequency. X is basically attrition, data is EMP data org, and statistics is percentage. So basically it will give us the percentage on the y-axis. If I don't put statistics as percentage, what it will give us is basically the count, right? We want the percent. So we see that most of the, like there's a large skew in the data. Most of the observations, around 80% or maybe more than that, are no, and only few of them are yes, right? So basically, we have in the target class that we are wanting to predict, we have a huge imbalance in our data set. So this generally leads to models that are not good enough because your model does not have enough data points from different classes or from different prediction types that you want to make to accurately learn anything from your data, any of these relations. So basically, uh, there's a large imbalance and we need to deal with that. So we'll be using something called SMOT, which is basically a oversampling technique. So what it will basically do is we have these few yeses. What we'll do is we'll basically sample from them with repetition again and again till we get as many yeses as many nos we have. So let's say I want to change this again to count. I say that there are let's say 220 yes data points and 1280 or something no data points. So what we'll do is we'll sample from the yes data points 1280 times. So instead of taking these 220, we'll take repetitions. So we'll sample something, we'll keep it back, we'll sample again randomly, and we'll generate a set of data 1280, which is same to the number of data points we have for no. And then we'll basically run our models on that. So what this does is basically it kind of extrapolates from the data that we have and tells our model that gives our model a more equally balanced data set to work on, which generally leads to better predictions. Okay. There's a unique problem with imbalanced data prediction, which I'll look at the end of the almost towards the end of this. So yeah, it's something to look forward to. Yeah. So the third step is basically doing exploratory data analysis. So first we need to see if there are any null data points or any null or missing values in the data set. So we need to fill them up. No. So what we do, EMP data org and info. So we get all the different columns. Now if I make it scrollable, I can see all of them have 1470 non-null. So basically all of them have, so total there are 1470 entries and all of them have 1470 non-null. So basically nothing, there are no null values in the data set. So we don't need to do any missing value imputation. So we'll move on to the next step. We'll visualize the categorical features and understand how different categorical features relate to attrition. Okay. So basically, for exploited data analysis, we are copying the data set. So EMP viz df, we are changing the name to this. Okay, so this is our data frame for visualization. We'll make a few changes to it. So first we'll add two features. One is called attrition yes, and the other is called attrition no. So attrition yes is one when the employee has uh, left the country, when the employee left the company, when the employee resigned, and zero when the employee did not resign. Attrition no is one when the employee didn't resign, and zero when the employee resigned. So basically, these are like inversions of each other. If there is one here, there should be zero here, and so on. Mm. So basically, what we are doing, we are taking the attrition column from our original data set, EMP with DF, and then we are mapping. So if the attrition is yes, give it a 1. If the attrition is no, give it a 0. So 1 means the employee has left. So we have this in the attrition yes. Similarly, in attrition no, we have no is 1, yes is 0. So 1 means employee did not leave. Okay. So now we'll just take a look at the data using head. We have age, attrition, business of travel, daily rate, uh, department, distance from home, education field, employee count, employee number, satisfaction, gender, hourly rate, job involvement, job level, job role, job satisfaction, marital status, monthly income, monthly rate, number of companies worked in, over 18, which is their age, overtime, do they do overtime, percentage salary hike, performance rating, relationship satisfaction, standard hours, stock option level, total working years, training times last year, work-life balance, years at company, years in current employer, years since last promotion, years with current manager, attrition, yes and no. Okay, so these are the last two things that we created, attrition yes and attrition no. And we again have our attrition here, which just has yes and no values. So basically what we have done is we have one hot encoded attrition. So now for each of the values, different unique values of attrition we had, we have different columns which have just 1 and 0. So this is basically one hot encoding, right? Then, yeah. So we'll get the names of all the categorical columns. So again, we'll select the data types. We'll include only object data. Then we'll get the column names from that data set. So this is basically a sub data set. From that, we'll get the columns name and we'll convert it to a list. And so we are getting all these column names: attrition, business travel, department, education field, gender, job role, marital status, over 18, and overtime. So these are our categorical features. Okay. So we'll make a function which will generate frequency graph, and then we'll basically call this function for for all of these different uh, column names, right? So it's easier than doing it again and again. So that's why we define a function, right? So the function is generate frequency graph, and we give it some column name. So we create a new data frame, temp group, which is basically the visualization data frame grouped by the column, and then we aggregate the sum across yes and no. Okay. So we are basically counting the number of attrition yes and the number of attrition no, depending on what is the value in the column name. So if the column name is, let's say, business travel, and there are three categories. So for each of the categories, we'll have three rows. Or each of the categories, we'll have three rows. Then we'll have two columns, attrition yes and attrition no, and we'll have the values for all of them. Right. Then we are creating another column called percentage attrition, which is basically what is the percentage of attrition. So attrition yes divided by attrition yes plus attrition no, whole thing into 100, basic percentage. Now we are printing it out. So we'll get a printout of this table. We'll see how it looks. Then we are making a bar plot. I think it's better if I run it once. So I'll run it for business travel. Okay. So this is a table that we got basically. So here what we are doing, we are grouping by the column name. So that becomes the index. Then we are aggregating the sum over these two columns. So these two columns, when we aggregate the sum, we are basically taking all the occurrences of one in these two columns. So it's basically the number of times or the frequency in at which one occurs or this category occurs, right? And percentage attrition is basically this divided by the total. So in this case, it will be 12 divided by 12 plus 138 into 100. It will be 69 divided by 69 plus 208 into 100 and so on. Okay. Next, we are making a bar plot where x-axis is the index. So it's basically business travel, this thing. And the height is given by the percentage attrition. So we are just plotting what is the percentage of attrition. And the Y label is the column name and the X label is the, sorry, I think this is wrong. X, it's Y, percentage attrition. Yeah. Huh. So basically what we have now is business travel. We have three categories: non-travel, travel frequently, travel rarely. And what is the percentage attrition in each category? So what this kind of visualization and this kind of calculation helps us achieve is that we now know if in like this categorical variable, which is business travel, if the different labels or the different categories that we have different rates of attrition. So that means somehow people who are traveling frequently, because they have such high rates of attrition compared to people who don't travel, maybe that is this travel thing is leading them to leave the company, right? So if there's a high imbalance between all these different categories that you might have in your feature, if there's a huge difference in the attrition percentage across these categories, that means this feature might be important for predicting attrition, right? So here we see that there's a huge gap. Basically, it's very high for travel frequently and very low for non-travel, and somewhere in between for travel rarely. Next, we look at the department, and here we can see that attrition is almost comparable in sales and human resources, but lower in research and development. So maybe people more in or people who are more present in human resources and sales are more likely to leave the company. Right. Then we look at gender. We see that, okay, it's almost the same 14, 17 across gender. Okay. Slight difference. Marital status, we see that single people mostly leave the company, whereas divorced and married people stay on. Over time, we see people who are doing overtime, which is yes here, have a very significantly high rate of attrition compared to people who don't do overtime, which is almost thrice the number in this case. Right. Then we look at education field. So yeah, we see that it's slightly higher for these three: human resources, marketing, and technical degree, while it's lower for the other categories, 5-10%. Yeah. Then we look at job role. So if you're a sales representative, you're very likely to leave the company because it's almost 40%. It's quite high. Then come laboratory technician and human resources at 25, and sales executive and research scientist at 15, and rest of them are fairly low. So yeah, so these are the different categorical features, and it seems like all of them have some or the other slight difference among the different labels that they have, or the different categories that they have, subcategories that they have. So I think we'll keep all of the variable just to take a look at it. Right. So next we'll look at all the different ordered categorical features. So ordered categorical feature is like education, where we have different levels such as 1 below college, 2 college, 3 bachelors, 4 masters, 5 doctors. And for example, like job satisfaction, which goes from 1 low, 2 medium, 3 high, 4 high, and so on. Right. So what we'll do, we'll again use the same function and we'll plot it. So here education has 5 labels, 1, 2, 3, 4, 5. So it gives us a plot of that. We see 1 and 3 are slightly higher than the rest. 1 and 3 is basically people who are below college or bachelor's education. They are more likely to leave. Then job satisfaction, as expected, if the job satisfaction is low, 1 is low, 4 is high. If job satisfaction is low, people are more likely to leave the company, right? So there's a change. Then work-life balance, 1 bad to 4 best. Okay. So again, work-life balance also, as your work-life balance increases, you are less likely to leave. However, if people have very good work-life balance, they tend to leave the company. Okay. Then environment satisfaction, this also, as it increases, people stop leaving. Job involvement again shows a similar curve, where basically low job involvement means the person is more likely to leave, and high in job involvement means the person might not leave easily. Yeah. Then we look at performance rating. So it has only two values in the different columns that we have. So 3 and 4, which is basically excellent and outstanding. and both of these are almost at the equal value. So maybe we can leave this out. Right, we'll take a call later. Then we talk about relationship satisfaction. Again, if you have low relationship satisfaction, you're more likely to leave the company, or it seems so. Okay. So from all these categorical numerical variables, I think percentage attrition, sorry, performance rating is something that we might not want, but the rest of the things seem like they're varying between the different subcategories. So yeah, we'll want to capture these variances and differences in our model. Great. Okay. So next we want to visualize numerical features. So generally, when we are applying any model, uh, it they tend to work well for predictions when our data distribution is normal. So when our data is normally distributed. If we have a skewed distribution, then the predictions that the model makes might not be good. So generally, what you want is basically normal distribution of your features. So if your features don't have a normal distribution, we can make it normal through log transformations, right? So here what we are doing, I'll just make it. We are basically making two histograms using plt.hist. In the first one, we are making for age, and the color is green. So you want to see the distribution of employee age, of course, the title, X label, and so on. So subplots we are making. 1 to 1 is basically this, 1 to 2 is basically this. In the second one, we have a histogram of monthly income. Okay, which is colored red. So here we can see that the employee age looks fairly normal. Okay, whereas the employee monthly income looks very skewed. It's not normal. It's mostly right skewed, right? A lot of data points towards the right tail. Then what we do, we'll plot the log transforms of these to compare. So basically, I have the same code. However, here I have np.log1p, which basically takes the log of these values in this column. Right. So now this is the distribution of log of age. Log employee age. That's okay. Anyways, it's log of employee age. Yeah. Then here we have for monthly income. And this more or less has become more symmetrical compared to this. But there's a mathematical method in which we can check. So basically, if we write a pandas column dot skew, it'll basically calculate the skewness of the column. So what we are doing here, we're calculating the skewness of both these features, age and monthly income. Okay, using dot skew function from pandas. And then we are again calculating the skewness after log transformation. So basically, we log transform the data set first and then take the skew. Okay, we run this. We see that the skewness for age is 0.4. So ideally for normal distribution, the skewness should be 0 because the distribution is symmetrical. It's not right or left bending, right? Whereas the skewness of employee monthly income is 1.3, of course, because it's heavily right skewed. A lot of values on the right tail, right? However, when we log transform, the skewness for age becomes minus 0.13 and for income becomes 0.28. So this becomes, all of them become closer to 0, which is what we ideally want in our predictive, in our features, right? So basically, however, like the skewness for age is still okay here because it's more or less symmetric. So we won't be transforming any skew, like all of the numerical features that we have to log of their values. We'll just do it for features that have very high skew values. So we'll set a cutoff for skew later and then go through all the numerical features that we have and then basically make log transformations. Right. Now, this next step is feature engineering. So here we are basically trying to make new features, right? So to be honest, this whole sample project I got from someone and I modified it. So basically, there are a couple things that they did that I don't agree with a lot. So I have modified a few bits of code here, but I have not changed all the wordings here. So be careful of that. Sorry. So basically, what we are doing here is feature engineering. We are trying to make new features that might be more informative. Okay. So one such feature is tenure per job. Okay. So basically, uh, people who have usually worked with many companies but for small periods will tend to leave early because they always need a change of place. Right. So this might be an important variable to predict attrition. Right. This years without change is something that I don't agree with, and it's something that we'll remove. And the next one is compensation ratio. So basically, it is the ratio of the actual pay that an employee is getting to the midpoint of the salary range for that department or organization or role, right? So it's basically like how much are you exactly getting and how much you should ideally get, right? So what we'll do for feature engineering, we again copy the data set. We write emp proc df. Okay, so this is the process df. The emp proc df tenure per job is initially 0, is set it to 0. Then we iterate through the data frame. So for I in range 0 to length of data frame. If the number of companies worked by that guy is greater than 0, what we do is in tenure per job, we write total working years divided by number of companies worked. Basically, we are taking an average. So this guy has worked for like say 10 years and in 2 companies. So on an average, he has worked for 5 years in both the companies. Things like that. It's a gross average that we are taking. Okay. I have written it as a for loop for making it easy to understand. In pandas, you can also uh, do something very short where you can use all these different columns by apply and everything, but it gets slightly complicated to explain. So I have done this. Okay. Then what we do, so we added our tenure per job variable, which is here. And then we want to add compensation ratio. So compensation ratio is basically we are taking the median income across the whole data set. Okay. And then what we are doing, we are dividing the monthly income of each employee by the monthly income median. Okay. So again, we print how many data set rows and columns are here. So we see we have increased the columns by 2. It was 35, now it's 37. And again, it has 1470 rows. So as mentioned before, we had some unwanted columns that we won't need for analysis, such as employee number, employee count, standard hours, and over 18. So we'll remove those columns. So we make a list, then we write emp proc df dot drop. So we are basically dropping these columns. We give it the name list. Axis is 1 because we are dropping columns, not indexes. In place equal to true. Okay, so that it drops actually, and it doesn't just return you a view. Then we print the dimensions of the data set. So now we have 33 columns because we dropped 4, we had 37, we are now having 33, right? Okay. So now what we are doing, we are separating our data frame into numerical and categorical different data frames so that it's easier to process them slightly separately. Then we'll again combine them later. because all these categorical variables we'll again have to change into some numerical form because our machine won't understand the categorical significance level, right? So what we do here, full column name is basically in the processing data frame. What are all the columns? So we are getting all the column names. Numerical column names will basically get the column names of numerical data because we are selecting data types and including only integers and float here. Okay, so we get a list of numerical feature names. Then this is categorical features, categorical ordered features. So basically education, environment, satisfaction, and all of the things that were like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so these things. Then our target variable will be attrition. So all the numerical column names will be all the numerical column names without the numerical categorical names, without the ordered categorical features, right? So this will again have the ordered categorical features because they are also integers, right? So what we want to do, we want to remove them. So we get a list, which is basically this column, these minus these columns, right? Then for categorical columns, we want to remove the target variable, which is attrition. Okay. And we want to remove all the numerical variables. So basically full column name minus numerical column name minus the target, right? So we have in this second data set, the categorical and the ordered categorical features, right? So these are the names of the features, not the features. Okay. Then we are printing the total number of numerical features, which is basically length of this list. And what is the total number of categorical and ordered categorical, which is length of this list. Then we'll extract it from the data set. So cat emp data frame is basically categorical features of the employee data frame. Num enp data frame is basically numerical features of the employee data frame. We have stored it as separately. We have 16 numerical features and 16 categorical features. Okay. And our target is attrition. So we talked about skewness. So we'll set a boundary for skewness, which is like 80%. So if a column has a skew greater than 0.8, okay, then what we'll do is we'll basically take the log. Right. So for column and numerical column names, or basically all the numerical columns, if column, if the in the numerical data set, we select the column, the series, if the skew is greater than 0.8, then we modify the column to log of that column, and then we print the head. So basically, some of these columns we have modified to log. Actually, if I run this again, we'll create it. So monthly income is one such column which had a very huge skew. So it has now converted into log of the values. So now the skew will be lesser, right? Then the next thing we need to do is we need to one-hot encode all the categorical features because we had categorical features like education, which is 1, 2, 3, 4, 5, which are different levels. So what we want is education 1, education 2, 3, 4, 5, all different columns. And in each column, each row value will be either 1 or 0, indicating that this category is like the data point belongs to this category or not, subcategory or not. Basically, we are iterating over columns in categorical column names. Then we are creating dummy columns. So call dummies is basically pd.getDummies, which is a function which basically does one-hot encoding. The thing that we did with dict vectorizer a few last class. So this was get dummies does. So we take the column and we create dummy variables from the column. Okay. And you have to give it a prefix. So prefix will basically will be added to the name of the column. And then we are adding this dummy column to the data frame. So we are getting a list of dummy variables, we are adding it to the data frame for each column. Then attrition target is basically our attrition variable. And here we are mapping yes and no to 1 and 0. So basically we are converting our attrition into another variable, into a numerical feature, which has just 1 or 0. If it's yes, it has 1. If it's no, it has 0. Right. After we do all this, we have created dummies and added it to our categorical variable table. However, we have not removed the original categorical variables that we had. So education, which has the values 1, 2, 3, 4, 5 on the rows, is still there, but we don't want it for our prediction. So what we'll do, we'll drop all these categorical columns that are initially there, because we have converted all of them to dummy columns. Okay. And most important, in place equal to true to actually remove it. And then we get the head. So what we'll do is, first I'll write. Okay. So initially we had education, which had 1, 2, 3, 4, 5, these values varying from this. Job involvement again, stock option, and these different travel frequency, travel rarely, and all. So now what we have in our data set is education 1, education 2, education 3, education 4, education 5. So all these different values have become different features. And each row value in each of these features is either true or false, depending on if the education value is true here or false here. Right. Similarly, for job involvement, for business travel, job role, everything is converted into this. Okay. Next, we want to, so basically we have converted all our categorical features into numerical or Boolean in this case, which is also numerical, like which works well with our model. So Boolean and numerical inputs are okay. So next, what we want to do is we want to see what is the correlation of different variables. So some variables that might be highly correlated, we'll have to remove. Okay. So we are numpy is basically the numerical part of the data frame that we had. This. So we are basically taking that into basically copying that. We need to copy that. Okay. So correlation DF is basically we are concatenating this numerical data frame with the attrition target. Remember, attrition target is basically data frame uh, pandas series with 1 and 0 based on the attrition variable. Right. We are adding it to our data frame, this data frame to create a correlation DF. Then we are calculating the correlation. Then we plot the figure. We create a zero matrix of this shape. Okay. Then so these are things that we might not need actually. Right. So these are present if you want to like have a triangular data frame. Sorry, a triangular matrix instead of a square matrix. So what we'll do is we'll just simply do a SNS heat map. We give it the data correlation this. Annotation equal to true. We want all the values here. Square equal to true. So it will make a square. Line width, we want 0.5. Minimum value is -1. Maximum value is +1. And the color map. So we see all the diagonals are highly correlated because these are the same variables. Hourly rate versus hourly rate, age versus age, and so on. And the last variable is attrition. We can see that the attrition is not really highly correlated with anything. Okay, but we see that this compensation ratio and monthly income are very highly correlated, 0.99. So we might face issues if we put these things in the model. So what we'll do, we'll remove that. Uh, so since the compensation ratio is something that we create and anything that matters more, we'll remove the monthly income. So we'll drop the monthly income column. So access we have to give one because we are dropping a column, and here you have to give a list with the name of the columns that you want to drop, and in place equal to true. So we are dropping it from the numerical data frame. Okay. And then we have our final data frame, which is basically a concatenation of our numerical data frame and our categorical data frame that we modified. So we are concatenating both of them along the columns, x is equal to 1. So it will horizontally add them basically. And then we print the dimensions of this new data frame using the shape variable, and we print the head. So we basically want to see the data frame also. So after treating, we have 1470 rows and we have 79 columns now. And note that all of these columns are either Boolean or numerical. Basically, this is perfectly ready to go into our model, right? So now that we have a list of process features and everything, we can actually move on to building a model. Actually, building a model. So since we have to predict a binary class, which is attrition, which will be yes or no binary, we'll be using classification models, which will basically take our data and try to predict if given these other features, if the attrition will be 1 or 0, right? So yeah, so we'll be using a classification model. We need to keep in mind that we need to have a better accuracy of predicting attrition. So if the company is actually, if the people are actually leaving, we want to know which people are more likely to leave. Okay. Uh, so basically, how we'll visualize all these results after we are done is we'll have a confusion matrix. Okay. So a confusion matrix in scikit-learn looks like this. So on the left-hand side, you have the actual results, 0 and 1. On the right-hand side, you have predicted results, 0 and 1. Right. So in our case, it's attrition. So attrition no, attrition yes, attrition no, attrition yes. Okay. So in basically, yes is 1, no is 0. So if actually the person has not left the company and our model predicts 0 or no attrition, that means our model, this prediction is a true negative. It was a negative prediction. The person did not leave the company, and we are predicting as such. True positive means the person left the company, and we are predicting that the person left the company. False positive is basically the person did not leave, and we are predicting that the person left. False negative is basically the person left, but we are predicting as not left. So false negative is actually negative, which is false. So it should actually be positive. And false positive is actually a negative, which is false, is actually a positive, which is false. So it should actually be negative. Right. So given a confusion matrix, there are different parameters that we can focus on. Okay. So overall, we can focus on the accuracy, which is basically true negatives plus true positives. So basically, these two, the diagonal things in a confusion matrix, are the correct classes and correct predictions. So no is predicted as no, yes is predicted as yes. So you want to maximize numbers that occur here. You want to minimize numbers that occur in false positive and false negative. Right. So accuracy is basically how often is their classifier correct on average. So basically true negative plus true positive divided by total number of observations, right? Because these are the correct observations and these are the incorrect observations, right? Then we have something called recall or the true positive rate. Okay. So when it is actually yes, how often does it predict yes? Okay. So basically true positive divided by true positive plus false negative. So if the data point is yes, how often does, like, how correctly does our model predict yes? Okay. So from all the yes that are there in the data set, how many is our model identifying basically? Right. We have precision, which is given by true positive plus false negative, false positive. Okay. So it's basically when our model is predicting that something is positive, how likely is it that it is positive? Right. So TP divided by TP plus FP. And we have specificity, which is basically uh, true negative divided by true negative plus false positive. So basically, when it is actually no, how often does our model identify that? Right. So we have these three things, which are composites, and we have the accuracy. Hmm. We will also look at some other features, such as the cross-validation score, which is basically when we are doing a k-fold cross-validation on our data set, as we talked about before, what is the mean accuracy of the model across all the different k-folds? Okay, we look at the F1 score. F1 score is basically the harmonic mean of the recall and the precision. So recall and precision we talked about here. Okay. Recall is basically TP by TP plus Fn. Precision is basically TP by TP plus FP. So this by this plus this was this by this plus this. These two quantities, you take the harmonic mean of that. So it tries to balance out both of them so that you are basically trying to put more points here and more points here from both these two categories. Okay, great. More points here and here. Great. Then we have the ROC curve, which is basically is actually a graph and a value, ROC value. So it's generally the graph is plotted by uh, plotting the performance of a classifier over all different thresholds that it can take. Okay. And then, so what is the true positive rate and what is the false positive rate? Okay, the sensitive recall and the specificity. Right. So it basically generates the values of these by assigning different thresholds to predictions of our model. Okay. And basically, it's the easiest thing to remember is that ROC value, the ROC area under curve, which is the ROC AUC value. I'll just show. Okay. So this is basically our ROC curve. It plots the false positive rate versus the true positive rate. Right. So the false positive rate is basically specificity, Tn by Tn plus Fp, and the true positive rate is basically uh, sensitivity, which is Tp by Tp plus Fn. It varies the threshold of predictions and then plots a graph like this. Right. Graph like this. So basically the dotted line you see here in all of these graphs is what a average random classifier would produce. Huh. What graphs that you get for your model will fall somewhere like this, somewhere on the curve. Other realistic graphs would look something like this for a sklearn, right? And the perfect classifier will have a graph that goes like this. So this is basically a perfect classifier. It goes from this 0 to 1 and then from 1 to 1. Okay. And AUC is basically what is the area under the curve. So as you might see here in these images, as your model gets better and better, the area that is there under the curve of your model increases. So if you have a higher area of curve, area under curve for ROC, for the ROC curve of your model, then your model performs better. So what we'll be using actually is not ROC curve, but ROC AUC value. Right. update this later. We'll be using ROC AUC value. So first what we need to do, we need to divide our data set again into testing and training and validation sets. So we import testing split. This we don't need. So what we do is we provide the final employee data frame, which is the process data frame. And the Y variable is the attrition target, which is a pandas series. We want it to divide into this 70-30 ratio. So 30% we want to keep for validation, 70% we want to keep for ourselves. Then we are writing what is the length of X10, what is the length of XY. Basically, what is the length of each data set. So training set has 1029 variables, data points, sorry, and validation set has 441 data points. Now we do y train value counts, y val value counts. So what this gives us is attrition, how many times it's 0, how many times it's 1 for the training data and for the testing data. Here also we can see there's a very high imbalance in the data, both for the training and the testing data set. The training data set we have around 900 and 200, 850 and 170, but yeah. So it's like around more than 4 times right in one category compared to the other where we are trying to predict, right? Again for test also the ratio is similar, right? So next we need to choose a few models to run our uh, classification. So we can take a look at these different links. So this is actually a good place to start. So this sklearn gives a uh, guide for you to choose the best uh, estimator or the best model for your task. So you start from here and you keep answering a series of questions. It's like a decision tree. You keep answering a series of questions and you arrive at a given model. So let's say we have 50 greater than 50 examples. Yes. We are predicting a category. Yes. Do we have label data? Yes. We have less than 100,000 samples. Yes. So linear support vector machines we should try. Then if it's not working, and if we have text data, we should go for naive Bayes. If we don't have text data, we go for k-neighbors classifier. If that is not working, we go for support vector machine and other ensemble classifiers such as random forest models, ADA boost, gradient boosted trees, and so on. Right. Second. The other thing is, so we can go that way. The other thing is we can also look at all the algorithms that are available for supervised learning. Okay. And like we see what are the different models that we have, what we can do with them. So for example, here we have logistic regression, which is a classification algorithm. We have support vector machines, which can do classification, stochastic gradient descent, nearest neighbor classification, naive Bayes, which can do all these things, decision trees, we do classification, random forest, bagging, etc. So we look at all the different models and then we end up selecting a few models. So for the sake of the course, we have selected a few models, which is logistic regression, uh, then random forest, decision tree, ADA boost, gradient boosting, and Gaussian naive Bayes and excited classifier. So these are all classification algorithms. We want to put them together and see how they perform. So we'll make all the necessary imports, okay, for running our models. Then first we'll define a few functions to evaluate the model performance so that we just run these functions and it'll automatically do things. So basically, this is a function called generate model performance. We are given actual target. So basically, actually what the prediction was, class prediction, attrition, yes or no, and what is the predicted target. So we are basically what our model predicts. We provided these two variables. Then what it does is, it first creates a confusion matrix, like the one that we talked about above here. Okay, using sklearn, it will create a confusion matrix using these two variables. So these two lists. Then we also get the ROC AUC score. So this is basically the area under the curve. We get the accuracy score using the accuracy score function. So these three functions come from sklearn. Okay, right. Then true positive is basically the confusion matrix where the value is actually 1 and it is predicted as 1. Right. 0, 0 is basically true negative. False positive is 0 predicted as 1. False negative is 1 predicted as 0. So we take all the values out. As per the definitions of sensitivity, specificity, precision, we write the formulas. So TP divided by TP plus Fn is sensitivity, Tn by Tn plus Fp is specificity, TP by TP plus Fp is precision. We multiply all of it by 100 to make it into percentage, and then we return all these variables. So this is basically a function to generate model performance. Right. Then we have another function called evaluate model score, which basically does the actual model thing. Right. So we provided some data, X train, Y train, X train, X test, Y test. So this is the training data, X and Y. This is the testing data, X and Y. And we have another variable scoring, which is by default accuracy, but it can change values, right? So we first create all these, instantiate all these different models. Logistic regression CV, random forest, XRTs, gradient booster, disjoint tree, adder boost, Gaussian knife base. We instantiate all of them, then we store all of them in a list, right? One after the other. So we have 8 models, right? Then we create a data frame called model results, where we have all the column names, model, accuracy, precision, cross-validation score, sensitivity, specificity, ROC, AUC. Let it be ROC score. Okay. Then what we are doing, we have to plot the confusion matrix. So we are creating a figure and axis with subplots, 2 into 4. So basically 2 rows and 4 columns. You'll have 8 plots. INJ are basically indices. Initially these are 0. So we iterate over all the models that are there in the models list. So for each model, we fit the training and testing data, X train, Y train. We fit the model. Then we make the Y predictions using the X test values, right? Then we use these prediction, Y-pred and the Y-test, which is the actual values, to generate the model performance, which gives us a sensitivity, specificity, accuracy, precision, and ROC score. Okay. Then we get the cross-validation score using the cross-val score function from sklearn. So we give it our model, we give it the training data, and we give it the what is the cross-validation. So this basically happens when cross-validation score is basically the score you get on your training data while you are training. So you're cross-validating it, right? Whereas for the rest of the things, we have used the test data to make the predictions to see if our model is like making good predictions on unseen data, right? Then to this model results, we are basically concatenating this model results and a new data frame, which we are creating. And basically storing it as model results. So in this new data frame, we have basically model, which is the model name. So if you type model dot underscore underscore class underscore underscore dot underscore underscore name, it'll give you the actual name of the model as defined by sklearn. Then the accuracy value is the accuracy that we get here, precision we get here. Cross-validation score is basically the, so this cross-validation score will return as a list of all the accuracy scores across the different cross-validation. So we are doing 5-fold cross-validation. So it means we'll get 5 values in the list. For each step of the cross-validation, what is the accuracy? So we take the mean of that and multiply it by 100 to get the cross-validation score as a percentage. You have the sensitivity, specificity again from here, ROC score from here. Then just index is 0, ignore index true. Then we use the confusion matrix formula from function from sklearn to again create a confusion matrix for the test and the predicted data. Labels are basically the labels of our data, which is yes or no, 1 or 0. So we are using model.classes, which is one of the parameters of each model where they store what are the different classes they are predicting. Normalize equal to true basically means that across all the true predictions, it will normalize. I'll tell you in detail. Then display. So basically, sklearn has another function called confusion matrix display, which can create a display for your confusion matrix. So you don't need to plot extra. So basically, we are creating a display and storing it in this. Then we have to plot it. So display dot plot will basically plot it to any axis that you give it. So we are giving it the axis j and I. So j and I are initially 0. Then we are setting the title as model is equal to model name. Right. Now, each time this for loop is run, if the value of I is less than 3, then we increase the value of I. Okay. Otherwise, if the value is greater than or equal to 3, then we write I equal to 0. We start from the beginning and then we increase j. So I basically is the column. So we are going filling is the first row, one column, second column, third column, fourth column. Then when the fourth column is done, we are basically going to the second row and starting over again. Then after all this model running and plotting, we show the results and we return model results. Right. We define this function. Now, model results here is basically, we call this function evaluate model score on our training and testing data that we had divided before. And we print out the results, model results. We'll get a plot and we'll also get a table or a data frame. Okay. So basically, this is our confusion matrix. So what did I mean when I said normalize equal to true? What it means basically is that across the rows here, across the true values, the things are normalized. So basically, if you add these two, it should come to 1. If you add these two, it should come to 1. It basically gives you a percentage across the rows. Right. So here we can see that, so ideally we want our diagonals to be, so the higher values are yellow and the lower values are blue. So we want our diagonals to be yellow and these opposite diagonal to be, main diagonal to be yellow and the opposite diagonal to be blue, right? However, you see that that is not the case. And for many of these models, for example, this logistic regression, random forest, and this extra trees, we see that both the sides, the lighter side or the lighter side is basically 0, right? So we can see uh, all the different variable values that we have. So what is the precision, recall, cross validation score, sensitivity, specificity, right? So note that the sensitivity is quite low here for the random forest. That is because most of the data points it's classifying as this. And this is basically one of the pitfalls of using a very imbalanced data set. So the thing is, you remember when we started out for our training and our testing data set, we have like 4 times as much values of 0 than 1, right? So what the model has learned is that if it always predicts a 0, on average, it will be wrong always whenever there's a 1, when the true label is 1. However, if it always predicts a 0, the accuracy value that it gets is quite high because the instances of 1 that you have in your data is not that much, right? So, for example, let's say in our testing data, we have 380 samples of 0 and 61 samples of 1. So if you create a model which predicts 0 for every data point it encounters, then on an average, it will have an accuracy of 61 divided by 380 plus 61 into 100. Sorry, it'll have an accuracy of 380 divided by 380 because it predicts everything as zero. It'll have an accuracy of on average of 86%, even if it just makes stupid predictions, which is just predicts one class. Right. So if you see the accuracy of random forest, it's somewhere close to 87 actually, right? And you see that most of these models are similar. So what truly sets apart different models is the ROC score. So if you get a ROC AOC which is quite high compared to other models, that means this model is doing better. So we'll take a look at this logistic regression CV model, which has the highest ROC AOC score, which is zero point 0.7. So here you can see that, okay, it's doing slightly better. But based on these confusion matrices, my gut tells me to go with this Gaussian naive Bayes model. Even though it's slightly worse off than other models, it looks better as if like it's trying to predict the right things. Right. If it had more data, it would have been better. That is the thought that comes to mind. So now what we'll do is, since we have this huge imbalance and these models are basically not trained properly, we'll do oversampling. So to do smooth, we have to install a package called imblearn, which is imbalance learn. So basically you do pip install imblearn. I've already done it, so it's already installed. So now from that package dot oversampling, we have to import the smooth algorithm. So we create a oversampler, we instantiate a oversampler, which is smooth. Here we are giving it a random state so that next time we run the thing, it again resamples the same way, right, across different times. So basically, we have to fit and resample over this whole data set, which is finally MP data frame and attrition target for the Y value. Okay, so it fits and resamples. So now we have X mode and Y mode, and we again split it using test train split. So X trans mode, X whiles mode, Y trans mode, Y whiles mode are the different things that we have now. Now we have training. What is the length of the training data? What is the length of the testing data? Just run this and we see training data, the length is 1029 and testing data, the length is 441 again, right? Now we also want to see this. Right. And we also want to see this. So basically now our data set is more balanced. We have, because we are oversampling, we are basically making both of the samples equal by sampling randomly from the class that has the lower count of values, right? So now our data set is more balanced. So now we basically run the function again, evaluate model score with the new data, which is training data smooth and testing data smooth, and we plot the results. Takes slightly takes some time because we are running a lot of different models. Now you see that the confusion matrices have come to life. So we have bright yellow confusion matrices on the main diagonal, bright yellow, and blue on the other diagonal. So basically, it means all of our models are performing quite well. And we can also see the change in the ROC score and the accuracy values, precision and sensitivity of each model compared to when we carried it out for the imbalance data. For example, here the sensitivity of the random forest classifier is 9. However, here sensitivity of the random forest is 87, which is quite a big jump. The accuracy values have also increased quite a fair bit. So it's from around 80 something and 70 something to 90 something and 80 something. The ROC curve has changed quite a bit and has increased quite a bit. From here, if you want to see the best model we get is logistic regression CV, which has a ROC score of 0.935. And we can see that the predictions that it's making is quite good quality. Now, if we if mm, we'll just take a look at the model. What was it? Logistic regression CV. So we go to logistic regression. Right. So it has different parameters now. Okay. So it has CS, fit intercept, penalty. So these solver. So these are the different parameters that we can vary now. So when we ran our models and everything, for each of these models, we just fit based on random parameters. So sklearn would have chosen some basic optimal, uh, like fairly optimized parameters, which are starting values, and then arrived at some uh, good model. So when we are comparing across different classifiers, we are basically using the random initializations of these and random hyperparameters. Not random, but basically sklearn provided hyperparameters. However, once we have decided that we want to probably use this model, logistic regression CV, because it has the highest accuracy of the RSAUC score and everything. So now what we need to do is basically we need to go look up what are the different parameters, hyperparameters that it has, and then how we can modify those hyperparameters, right? So how we can tune those hyperparameters using grid search CV and everything to make even more better models. So can we push this accuracy of 93% to more, 93.5 to more? So I leave you with that thought. So this sample project is done. For now, we compared different models, we processed the data, we did feature engineering, we looked at different data distributions, we plotted a lot of variables, looked at some stats, and then we ran some classification models, and then we finally arrived at this logistic regression CV model, which might be the best model for this case. So next, what we should do is tune its hyperparameter so that it makes even better predictions. So that's something I urge you to do using knowledge that you have gained from the grid search CV lecture that we had, sklearn lecture last class. So based on that, I think yeah, so that would be good practice for you. Apart from that, mm, here are some bonus projects that you can try out. So for the project that we carried out, we asked a simple question. Given these characteristics of the employee, will they resign or not? So basically, given these characteristics, classify them as a person who will resign or a person who will not. Right. Uh, the other things that we can ask, such as how experienced are the employees that are leaving? So are more experienced employees leaving more, or new recruits leaving more? Which job roles or education fields are more likely to lose employees. And we can think of such other different variables or questions that we want. And then you can think of how to approach them and try to figure out possible models that you can run so that to make some predictions or make some clustering. So instead of this predictions, we can just remove the attrition variable that we have in our data set and just make it a clustering problem. So, for example, we want to see if this yes and no people that are there, people who are leaving the company and people who are not leaving the company, do they cluster together? Are there certain uh, features that are common between them? Right. So we can see, we could have just seen that clustering and all. Right. So there are countless questions that you can form and countless questions that you can try to answer. Right. Again, if you go here and if you go to discussions or if you go to code, then people have a lot of different questions. Uh, People have a lot of different analysis that they have done, exploratory data analysis, with different kinds of models. You can use these data sets to learn more about different models and how they work also, right? Apart from that, there are two more data sets that are freely available online. So I leave you with these two questions. So the first data set is house price prediction. So the data set is the Ames housing data set compiled for data science education. So like it's an expanded version of the Boston housing data set that was there before. You can download it from here. So I provided a link. So if you go to Kaggle and you find this, so basically there are a lot of different data fields, a lot of different 79, I think, different predictor variables and basically expanded variables and basically what is the final price. So it also has a row where it tells what is the final price of the house. Sorry, sale price and other such columns, everything else. So basically the objective here is to predict the final price of a home given all these explanatory variables. So basically here again you have to fit a classifier model where given such different feature values, you have to predict what is the price of the house. Not a classification, sorry, a regression model, which basically gives you numerical outputs, not class data, right? So this is a regression example that you can carry out. You can do a clustering example from this sample data set that we use, the IBM data set. The third question is basically, it's a Titanic passenger detail data set. Can be found here basically. It's a link again on Kaggle. So basically you are given different variables uh, such as survival, ticket class, sex, age, fare, which cabin they were in, which port they boarded, and everything. And then whether that person is alive or not. Okay. So there's one column which is basically if that person survived or not. Yes or no. Right. Uh, the class, the number of siblings they had, and everything. So basically, here the question is hypothetically, which kinds of people are more likely to survive on the Titanic? Does the socioeconomic class matter? Does the gender matter? Does the age matter? Things like that. For example, when we watched the Titanic movie, you would have seen that when they were loading lifeboats, they were most likely filling women and children first. So the age and the gender are things that might matter, right? Socioeconomic class is basically where you were. So if you are a worker in the ship, you're probably doomed because no one cares about you. But if you're a wealthy person, you have money and connections and everything, you're more likely to escape. People are more likely to offer you a lifeboat. Right. So things like this. And basically what all different features are can help you better predict if a person will survive or not. So this again is a classification example that you can try out. So these are the three bonus projects for the course that I would suggest. Apart from that, we talked about a lot of different things throughout the course. We talked about, so if I go to the website, which has been updated. So we in module one, we talked about data types and operation data structures. And we talked about conditional flow, control flow, conditions, functions. We talked about different packages in Python, such as numpy, numpy, which we use to basically work with arrays and data frames, arrays and data, numerical data. Pandas is something we use to organize and keep data frames for our data science projects. Matplotlib is a data library we use to plot. Seaborn is basically a easier library than Matplotlib for making complex visualizations. Then we talked about sklearn and proper data science and how to basically do data science, run your models. Then at the end, we had a sample project, right? So in the website, I'll be uploading all the lectures, not the questions, all lecture material that was there, and the final module will just be this. I'll not be posting the notebook for the final thing that we did here, sample project, because I would urge you people or anyone who is looking at the website to do it on their own. However, if later I feel the need, I'll upload it. Apart from that, rest of the things will be uploaded. The lecture videos will be uploaded to YouTube. If anyone has any questions, then this is a good time to basically ask them. If not, if you have any questions later ever, then you can basically uh, email me or yeah, basically email me if you have any more issues or anything regarding to this course, regarding to any project that you are trying out. Feel free to approach. You can also go to the YouTube videos and leave out comments if you want. If you are stuck in something, I can help you there also. So that's it for this course. Thank you for attending. Thanks, Abhishek. Yeah. And I'll hopefully meet you sometime later, someday, hopefully. Uh, and yeah, I think that's it for the quiz. It was nice having you people. Take care and goodbye.